block on a spring, you compress the spring, shoots off. It's like a spring toy, like a spring gun. Shoots off and it lands some distance away. Time elapsed. Projectile motion, y direction. Initial velocity in the y is 0. Negative h is 1/2 negative g t squared. You don't want to put in 9.8 here, specifically when it says put g in. Positives, 2gh root equals time. Two h over g. Yeah, that would have been problematic later on. I think the answer here is attractive in the end, so we'll see. So that's the time. Keep that in mind over here. Root 2h. Horizontal component just before it hits the floor. How fast is it going in the x direction? Projectile, x direction. Probably a good place to start. Almost all projectile motions use that equation twice. So it's a good place to start. How far did it go? Gives it to us. Distance d, initial velocity is whatever it is, and that's the time it took in order to get to the floor. Root 2h over g. So, initial velocity. G over root 2h over g. That's how fast it was going when it left. That's how fast it was going the x direction when it got down to the ground. Remember, the x direction velocity never changes. So if you can figure out the velocity at any point, it's the same velocity at every other. It's the same horizontal velocity at every other point. Work done on the block by the spring. It's an energy question. So you ask yourself, where do we start and where do we finish? Well, if we're figuring out work done by spring, one half kx squared, or work in general, is the change in energy. So if we can figure out either one of those two things, we can figure out how much work the spring did. This is going to be hard because we don't have k. So we cannot use that equation in this part. Without the spring constant, we can't use anything with the spring constant. And there's no way to figure out the spring constant because the next part says, what's the spring constant? So you're expected not to know it at this point. So you have to look at the only other way we know how to solve for energy, or work rather, and that is the change in energy. Well, what's changing energy here? What's the only thing in the question that could possibly change energy? Block. Well, if the spring is it's pushed towards the end of the spring and it's released, how much energy did that block start with? If I compress this block against the spring and then release it, how much energy did the block start with? The block's initial energy is 0. I compressed it. Now the spring got some energy when I compressed the spring, but as far as the block is concerned, the block started with 0 energy. Well, how much energy did the block finish with? Did it have 0 at the end as well? No, it gains some energy. It's moving. So it's moving after it gets released from the spring. That's how fast it's moving. So basically what we've done here is identified two positions. One where the spring is compressed, and one after it's gone. At the first part we could potentially have all these things. At the end we could have all these things. We're going to conveniently call, for this part, h equals 0. You could say h equals h, that's fine. You could leave it all in there. It's going to eliminate itself now. Its kinetic energy when it starts is 0. Its spring potential is that. 0. Its kinetic is 1/2 mv squared. Its spring is 0. So it went from this much work, or that much energy to that much energy. Well, work is change in energy, so 1/2 mv squared. What's its velocity? Oh gosh, what was that? D over root 2g 2h. 1/2 mass d squared over 2h over g. And you can go through with the rest of that problem. Spring constant, 1/2 kx squared equals 1/2 v squared. And 1/2 mv squared over x squared. Leave your labs before you take off today. You can just leave them on your desk. I'll come around and get them.